Hello, my name is Yang Gu. In this video, I will discuss my medical insurance price prediction model for the M3 Practice Hackathon. The dataset contains 1,338 samples with 6 features. Its age, sex, BMI, number of children, smoking status, and region. The target variable is insurance charges, which ranges from about $1,000 to $60,000. The evaluation matrix is mean squared error. And I took a systematic approach to improve performance. The first, I encoded categorical variable, sex, was encoded as a male equals 0 and female equals 1. And smoker was encoded as a no equals 0 and yes equals 1. Regions was encoded as a northwest equals 0 and northeast equals 1, southeast equals 2, and southwest equals 3. Then I applied standard scalar to normalize all features to have mean 0 and standard deviation 1. This ensures that fair comparison across models and helps gradient-based optimization coverage faster. And I compared 4 regression models. Here are the exact results. Linear regression, I got an MSE of 33.7 million, RMSE of 5,808, R squared of 0.782. And this model assumed a linear relationship between features and target, which is too simple for this data. And the ridge regression. I got an MSE of 33.7 million and RMSE of 5,808, R squared of 0.782, and reach as L2 regularization to prevent overfitting. But since the relationship is nonlinear, it doesn't help much. And for the next one, it's random forest. I got an MSE of 21.1 million and RMSE of 4,594 and R squared of 0.864. This is an example of decision tree using bagging, where each tree is trained on a random subset of data. For the last one, also the best performance one, is gradient boosting. The MSE, I got an MSE of 18.7 million, an RMSE of 4,330, and R squared of 0.879. This achieved the best performance of all these 4. And for the gradient boosting using that technique called boosting, which is different from random forest bagging. In boosting, trees are trained sequentially and uh, and uh, um, and each new tree focus on correcting the errors of residues of the previous trees. The final prediction is the sum of all trees predictions and weighted by a learning rate. And this works well for insurance data because the relationship between features and charges is nonlinear. And for example, a smoker pays significantly more than a non-smoker. And this effect is amplified when combined with high BMI. Gradient boosting can capture these complex interaction effects. And I used five-fold crossed validation to get a reliable performance estimate. The data is split into 5 equal parts, and the model is trained on 4 parts and tested on 1 part, repeated 5 times. My cross validation RMSC was 4,565 with a standard deviation of 379. The low standard deviation indicates that stable performance across different data splits. To assess model fit, I use a learning curve, which is a diagnostic tool for understanding bias and various trade-off. A learning curve plots training error and validation error against training set size. It helps diagnose these 3 scenarios. And first one is overfitting. The training error is very low and validation error is very high, and these are a large gap between them. And this means the model memorized the training data but cannot generalize. Second, the underfitting. The both training and validation error are high and don't improve with more data. This means the model is too simple. And third one is good fit. The training error and validation error covered as training size increases with a reasonable gap between them. And looking at my learning curve, the blue line shows the training MSE started at about 0.5 million with a small training size and increases to about 14 million as training size grows. This increase is normal because it's hard to fit more data perfectly. And the orange line shows that cross-validation MSE. It started at about 29 million with a small training size and decreases to about like 21 million as training size grows. This decrease shows that model generalized better with more training data. And the key observation is that the two lines are converging. At the largest training size, training MSE is 14 million and CV MSE is 21 million. The ratio is 1.5 times, which is acceptable. And if I had used a more complex model like random forest with 500 trees and no depth limit, we would see server overfitting. In that case, the training MSE would be around like 3 million, but CV MSE would be around 23 million, a ratio of 7 times. The large gap indicates that the model memorized training data. And my Gaussian boosting model with 100 estimator shows that much better generalization with a ratio of only 1.5 times. And the converging learning curve tells me that adding more training data will likely improve performance further. The model is not overfitting severely, but there is still some gaps between training and validation error, which is accepted for any real-world model. And in summary, I built a Gaussian boosting regressor that achieved the MSE of 18.7 million, RMSE of 4,330, R squared of 0.879. To improve in performance, I compared 4 models, applied feature scaling, and selected the best model based on the cross-validation. To assess model fit, I analyzed the learning curve. It shows good convergence without server overfitting. The gap between training and validation there is about 1.5 times, indicating reasonable generalization. And my prediction have been submitted to Kaggle in the required format. And thank you for watching.